Hi, in this video we are going to prove this identity which I've encountered while studying spectral graph theory and want to share it with you. Now let us start by defining what X and L means. So X is basically a vector and L is a Laplacian matrix. And what is Laplacian matrix? So Laplacian matrix is defined as D minus A. But what is D and what is A? Well, D is the degree matrix and A is the adjacency matrix. So in graph theory, assume that we have this simple graph. Um, this is vertex 1, vertex 2. Let's say vertex 3 and vertex 4. Well, so for the degree matrix is basically a matrix that we can see the degree of every vertex. In this case, the vertex 1 has just a single edge, which means it has a single the degree of vertex 1 is the degree of vertex 1 is 1, so we put 1. For vertex 2 it has 3 edges connected to it, so the degree is going to be 3. We are writing this to the diagonal. Vertex 3, it has a degree of 2, so we put 2, and vertex 4 2, and the remaining spaces are going to be 0. So this is how we define the degree matrix. What about the adjacency matrix? Well, this is important because it is widely used in graph theory. So the adjacency matrix basically indicates which vertex is connected to which vertex. In this case, we are at the first row and first column. So we look at vertex 1. Is vertex 1, the first row, connected to the vertex 1, first column? Well, no. So we are not assuming that there are any loops. There are no loops, so it is not. So we put 0. And by this logic, the diagonal should be 0 because no vertex will be connected to itself by a direct edge, by a single edge. What about vertex 1 and vertex 2? The first row, vertex 1. The second column, vertex 2. Are vertex 1 and vertex 2 connected by a single edge? Yes, they are. So the vertex 1 and vertex 2 should be 1. Similarly, this is also going to be 1 because this is the second row, first column, meaning vertex 2 and vertex 1 are connected. Similarly, the first row and the second column, meaning vertex 1 and vertex 2 are connected. So what we can infer from this is that our matrix, adjacency matrix, is going to be symmetrical along the diagonal. Similarly, the degree matrix is also symmetrical through its diagonal. Cool. What about vertex 1 and vertex 3? Well, they are connected somehow, but it's not a single edge, so we put 0. And vertex 1 and vertex 4 aren't connected, we put 0. Similarly, we put zeros in here and here too. And what about vertex 2 and vertex 3? They are connected by a direct single edge. Vertex 2 and vertex 4, they are connected. Similarly, this is going to be 1, 1. Vertex 3 and vertex 4 are connected. 1 and 1. So this is our adjacency matrix. So yeah. So the adjacency matrix is when you subtract both of them. So we just do matrix subtraction. 1, negative 1, 0, 0, negative 1, 3, negative 1, negative 1, 0, negative 1, 2, negative 1, and then 0, negative 1, negative 1, and 2, and realize that our Laplacian matrix is also symmetrical too. Cool. Now, let us continue from our original statement, and which states that x xt lx. Well, this is going to be equals to. by using some simple linear algebra, we can see that we can actually write this explicitly using this sigma summation n, and assuming Laplacian matrix is n by n matrix, obviously. Xi Laplacian matrix ij and xj. Cool. So we basically iterate over every row and column, and in this way we can write this formula, but this is not simple, right? We need some sigma summation, we need to iterate over every element. This takes long. We want to simplify it, and to simplify it, what we can do is we can divide this statement into two different cases. First case, I equals to j. Second case, I is not equals to j. Well, when I equals to j, right, we can write our statement as by statement I mean this one now. We can write it as I equals to 1 to n, and well, I Laplacian matrix I xi squared, right? Because I is equal to j. We just plug various cj as I and we iterate I over 1 to n. Cool. Then what we can write we can write this as I is equals to 1 to n. The degree matrix I actually let's use small I d xi squared. Why did I write d instead of l? Well, because we can see that the adjacency matrix, the diagonal of the adjacency matrix, is always going to be 0. By definition, so this is going to be 0. Because we are working with L row and column, the row and the row number and the row column are the same. The adjacency matrix is going to be canceling out, so we are left with the degree matrix. So instead of the Laplacian matrix, we can use the degree matrix. Oops, that is why we wrote that. Cool. Now let us continue when they are not equal to each other. In this case, we will have our original statement, but we can actually simplify it by using the adjacency matrix. So we can say I equals to 1 to n, j equals to 1 to n, xi, and this is important. We say minus a ij xj. Now the only thing I did was to swap Laplacian matrix is I and j with minus adjacency matrix ij. Why? Because this again by definition. Now, because I and j are not equals to each other, we are not working along the main diagonal, right? We aren't working with the main diagonal. And by the definition of the degree matrix, the remaining places are going to be 0, right? So the degree matrix is going to be just 0. So we are left with minus a here, since this just cancels itself out. It's just 0. So we are left with minus a. That is why we put minus a ij. And we can actually write this as just putting the minus outside. Sorry about that. I forgot another summation. J equals to 1 n ijxixj. Great. Now we are going to simplify this expression where I and j are equals to each other further. And to simplify it, again, we are going to use the adjacency matrix. So I'm just going to write out the expression and then explain it. Why? x1 to n xi squared. Well, This is, I just copied it from the above, and here is where things get tricky. 1 to n, adjacency matrix I j. Now what is this? Well, the only thing I did was to swap this degree matrices the specific location, with this summation. But how did I do that? Well, again, it is from definition, but not exactly. Well, you see, the degree matrix. So, for example, in this case, let's go from the first row, right? Or let's go from the second row. Um, so in the degree matrix, in the second row and second column, we have 3, indicating that vertex 2 has 3 edges, right? Cool. Now, in our expression where we wrote for the adjacency matrix, for that specific row, iterate over every column, right? And for adjacency matrix, by definition, as we said, if that row and that column has a edge between them, connecting them together, we put 1, indicating that they are connected. So for a specific row, if we sum up every column, which we are summing up ones and zeros, and then we are going to get the degree of that vertex, right? Because 2 and 1 are connected, right? Vertex 2 and vertex 1. Vertex 2 and vertex 3 are connected. Vertex 2 and vertex 4 are connected. So when we sum up all of these together, we actually get the degree of vertex 2, which we wrote it in here. That is why we swapped out the degree of the specific row and specific column, or the degree of our specific vertex, with an expression. We can write it from the adjacency matrix. I'm also writing, so yeah. And here, what we can do is we can actually pull out the summation out. So we can write it as n I equals to 1 j. Oops, this is gonna be equal j n adjacency matrix and xi squared. Let's also write the other expression here, minus, and so and great. Now we wrote our expression, which is basically equals to our original expression, right? And x. Cool. So this is where things get beautiful, because since the both summations have I and j that goes to n, we can actually merge them together into a single summation. So this whole expression is actually going to be equals to and summation I equals to 1 to n, right? We can merge them together, and by taking the adjacency matrix ij parentheses, we can write this ix squared minus xij. Great. Now we merge them together and we have another expression, but it doesn't quite look like our main expression that we need to prove. So in our main expression, as you can see, we have edges, right? This basically denotes for the edge, the unique edges of a specific graph. But how can we write out edges from this expression? Well, just realize that the adjacency matrix can only be ones and zeros. When it is 0, the summation is going to be 0, right? And when it is 1, we are adding those ones up together. Cool. We are adding ones together. Now, what we can do is assume that for a and j equals to 1, because for 0 it's just trivial, it's going to be 0. We can have I and j pair where vi is connected to vj, right? These two are connected. We can also have a j and I pair where vj is connected to vi. So when we are iterating over every element of our adjacency matrix, we are actually counting the same edge twice with I and j swapped with each other. We also said in the beginning of the video, adjacency matrix is symmetrical too, so we can also infer this I and j swapping them with each other from that symmetrical property too. But in this case, we are counting the same edge twice, right? So let's say for the same edge, right? Let's calculate this expression for a given same edge. So let's say for a specific edge where vertex I and vertex T are connected through a single edge, we have the expression, well, aij is going to be 1, so it's again trivial to write multiplied by 1. We are going to have, right? We are going to have, oops, yeah, xi squared minus xij from our summation. For j and I, where we swap I and j with each other, we are going to have xj squared minus xjxi. Now, since we are adding these two up in our summation, we are going to have xi squared minus 2xij plus xj squared, which is actually equals to xi minus xj squared. That is beautiful, because now we can write our original expression as summation for I and j pairs, distinct I and j pairs in our graph G that specify some distinct edges. We are going to have xi minus xj squared, which will be equals to our main expression, and that is the end of the proof. Well, I think this proof is worth sharing because it is interesting to know the Laplacian matrix, the vectors transforming, and well, yeah, I hope this video was helpful, and if you have any question, please leave a comment and have a great day.